We're live. Okay, Stephen, if you'd like to start us off, please.
Thank you. Hello, everyone, and welcome to today's event on Resilient Time for the Future for Telecoms. I'm Steve Douglas from Sparent Communications, and I will be your moderator. Today's event is split across two parts. In the first part, first hour, our distinguished speakers will be providing an overview of timing in telecoms. And in the second hour, we will have 4 technical focus sessions. The talks are pre-recorded for quality purposes, but there will be 2 live Q&A sessions with the speakers at the end of each of the parts. So please submit questions throughout using the Q&A facility on the webinar tool, and we're going to try to answer as many as possible live. Otherwise, we will publish responses at the end of the event. Now, to officially welcome you to the webinar series and introduce you to the National Timing Centre, I have the privilege now to hand over to Dr. Leon Lobo, who is the head of the National Timing Centre programme from NPL, the UK's National Metrology Institute. Let's hear from Dr. Leon.
Thank you very much, Steve. I'm Leon Lobo, and I'm leading the newly formed National Timing Centre programme at the National Physical Laboratory in the UK. Welcome to the first in our webinar series on Resilient Time for the Future, this one concentrating on future communications and supported by BT. Now, across sectors, our dependency on GNSS, which is a key capability for global position, navigation and time, is rapidly increasing. The UK government Blackett report on satellite dependencies for position and time highlighted this, but even more important, also highlighted the lack of awareness of this dependency, and this is especially true for time. Timing and synchronization is an underpinning capability, as you all know, in this sector and across digital infrastructures, and is essentially an invisible utility feeding applications such as phase synchronization of the energy grids, network sync in telecoms and broadcast, through to traceable timestamping for regulatory compliance in the financial sector. Now, the National Timing Centre will be developing a national capability for resilient time, and this would be even more important as emerging applications such as autonomous vehicles, AI, smart cities, factories of the future, and sensor networks, etc., go mainstream. And the NTC will help realize this. If you move on to the next slide, please, Paris. Now, recognizing the current requirement, the dependency on GNSS and the evolving threat landscape, the UK government has funded this NPL-led 5-year £36 million National Timing Centre programme, which is an R&D program to develop the resilient capability for the UK towards a resilient, assured time for the future. To the next slide, please, Paris. Now, the NTC program has three primary objectives. The first one is very much around resilience and securing the national timescale that is UTC NPL by putting in place a geographically distributed capability and connecting them. Now, Setnam Shima, one of our speakers, will go into a little bit more detail on this particular element later on in the webinar. Our second objective is very much around innovation and engaging industry and academia to stimulate the development of a supply chain for timing products and services in the country. And over the next few months, we are starting to shape and kick off funded innovation calls to industry and academia to the tune of £6.7 million. And finally, the element of skills, education and training is right up there as well as a key piece for this program, where we'll be assessing and addressing the skills gap for timing and putting in place everything from training courses, degree modules, apprenticeships, secondments and the like. And to the next slide, please, Paris. Now, the National Timing Centre program is a significant step towards an enduring, resilient capability in order to protect our digital landscape and develop new opportunities based on resilient time. And we're really, really keen for you to be involved to shape how the NTC could deliver these outcomes and benefit your businesses. Please consider what you see as opportunities for your business by having access to better time and frequency. We'll be hosting a series of focused workshops. There's a thought leadership panel session, the first being at ITSF on the 15th of October, as well as future webinars in this series. Please do engage, get in touch with your thoughts and ideas, or if you have any questions. Enjoy the webinar. Thank you very much, and back to you, Steve.
Thank you, Dr. Leon. And it's great to learn about the National Timing Centre programme and its role in supporting and developing UK skills. And now for our first talk on the history of time and frequency in telecoms from Mike Gilson. Now, Mike is a senior manager of synchronisation platforms at British Telecom and has played a major role in BT's synchronisation strategy since 1988. He currently leads a team responsible for all of BT's timing and design and development, so there's no better person to give us an introduction and history on time and frequency in telecoms. So let's hear from Mike.
The National Timing Centre is a bold initiative with many potential positives for the benefit of the UK. At its heart, securing and providing access to the key national resource of time and frequency. Communications has a key part to play, and given that, I am very pleased and proud to have been asked to open this session in the first of a series of webinars. BT and its predecessor companies have been involved in timing right from the beginning of the company, from the start of modern communications and continue through to this day. It is a great honour to have a job that can be traced back in our company from 1846 and to provide some history and insight into time and frequency in telecoms. In this presentation, I will cover a historical perspective, look at some of the recent standards and their implementation, look at the user cases and the applications, and then select a couple of areas for future development and exploitation. With the invention of the pendulum clock in the 1650s and the work of John Flamsteed, it was possible to work out the relationship between mean clock time and solar time. He was appointed as the first astronomer royal and moved into the new Royal Observatory in Greenwich. Here he could set the best pendulum clocks installed and set them to record local time. That is the average time when the sun crossed the meridian at Greenwich. The first Greenwich time was only really important to astronomers, but the growth in maritime trade and issues with navigation required changes. This resulted in the 18th century quest to determine longitude and development of chronometers and the setting of ships' clocks from the Greenwich clocks. On land, until the mid-19th century, towns kept their own local time, defined by the sun. There was no national or international conventions which set how time should be measured, and no standard timings for when the day would begin and end. But again, technical progress, trade and the movement of people pushed for solutions. With the expansion of the railway networks, communications also needed to keep pace, resulting in the need for national and also international time standards. British Railway Company started introducing a single time with the GMT, ultimately adopted across Great Britain by the Railway Clearing House in December 1847, and it officially became railway time. By the mid-1850s, almost all public clocks in Britain were set to Greenwich Mean Time, and it finally became Britain's legal time standard in 1880. The alignment of clocks on an international scale came about in 1884, and the Greenwich Meridian was recommended as the prime meridian. At this point, nearly 3/4 of the world's commerce depended on sea charts which used Greenwich as the prime meridian, so the argument was that this would be of value to the largest number of people. As a reference for GMT, the prime meridian at Greenwich therefore became the centre of world time and the basis for the global system of time zones before the invention of the cesium atomic clock and the development of coordinated universal time being adopted in 1972. BT has a long history of distribution of timing, right from the very earliest days as the Electric Telegraph Company in 1846. From 1852, the Central Telegraph Office received an hourly signal from the Greenwich Observatory and transmitted this at 10 AM daily to telegraph officers to time telegraph officers, post officers, and also provide timing for the railways. Later in the 19th century, various work was done on, and early 20th century, various work was done on looking at how correct time is distributed and the periodic synchronization of post office clocks from the parent clock at the Royal Observatory. In 1913, the Post Office sets up a service known as synchronization. But not only did we carry our own timing, we also carried timing for other people. And one notable circuit was the Post Office connection between the Royal Observatory to the BBC to carry the 6 pips. And the 6 pips are still broadcast on the radio today. A lot of work was done on the comparison of primary standards held by the Post Office at Dollis Hill and various radio stations and monitoring stations to the NPLO standard and against the Royal Observatory standards to monitor for error. And also work was carried out to synchronise the Post Office transmitter at Rugby with the National Physics Laboratory cesium frequency standards that had first been developed in 1955 by NPL. On this slide, I've tried to develop a timeline of master clocks and references used in BT over the last 120 years. On the left, we can see in the earliest days the first post office frequency standard in 1920, but before that there were many mechanical and electrical clocks. These were still in service till about 1930 onwards, and in 1930 there was 11,000 mechanical and 7,000 electrical clocks. Electrical clocks were specified to maintain time to within less than 8 seconds deviation over a week. Through the 20s, 30s and 40s, various systems were developed for frequency division multiplexing based on tuning forks and crystal oscillators. And a lot of work was done during the war on the development of crystal oscillators and the vacuum tubes to divide the frequency. In the 1950s, BT, or Post Office as it was then, worked closely with the National Physics Laboratory development of the crystal ring oscillators, and these were used to time the Rugby transmitter, and they were also synchronized to the National Physics Laboratory's new cesium standard. By the 1970s, the development of TDM and PSTN 64K voice switching required very tight synchronization, and this required the use of cesium oscillators. And this was deployed as a master-slave mutual synchronization network. By the 1990s, this cesium system had been replaced with a GPS-based system, and GPS continues to be the basis of timing used today with cesium protection. Various developments of clocks are ongoing, some steered, and enhanced network clocks are also being looked at. And if we look out to 2030, there's probably a good chance of clocks with the performance of part and 10 to the 16 being standardized and commercially available. So what we can see over that 120, 20, 30 years is an order of magnitude of improvement per decade. And the one thing to note also, as we start to get to clocks of the parts intended to be 16 or parts intended to be 18, that the altitude and the gravitational time dilation starts to become a significant factor we need to consider. This very generalized slide shows aspects of network and resource convergence from a timing perspective. First of all, the timing only needs to be sufficient for the service. And the table shows a very generalized view of ranges of time and frequency accuracy. Tighter requirements and capability will always exist. Secondly, from a network technology perspective, accurate timing is not always needed for the correct operation of the technology. In some cases, it's needed network-wide, in other cases, point-to-point. Just needs to be sufficient for the service carried. And Ethernet and packet network technology has not fundamentally needed timing, but has been shown to be very adaptable to provide high performance timing transport. Thirdly, from a timing resource perspective, owned master clocks are increasingly being brought together on a combined platform rather than being separate items of resource. And fourthly, timescales. Originally, these were a federated mix of local GMT and NPLO type timescales. Increasingly in recent years, these have been derived from UTC, either owned cesiums or GPS for frequency, or UTC GPS from an off-air perspective. Getting the standards correct and the right standards implementation is very important to allow us to develop the timing capabilities on some new and quite complex technology. And having a standardized architecture and operation for use in the telecoms environment with well understood practices built upon robust and resilient IP, Ethernet and optical technology is important. And how we've achieved this is by working through the ITU and working through the IEEE. The IEEE has developed a timing protocol called 1588, and within ITU we've profiled that and we developed the architectures and the performance requirements and the interfaces. This allows equipment to interoperate and interwork, and that's important because compliant equipment should operate seamlessly and to standardized performance levels, which allows us to build the network. And as part of these standards, we have various traceability and performance information that's passed through the network. And you can see below there are various standard streams that are linked together across various standards bodies and even industries. So some of the profiles that have come out of this work is obviously what's called a telecoms profile, which is what we use in the telecoms network. But there's also a power profile that's used in the electrical distribution network. And CERN developed their own implementation called White Rabbit that's used to run the Large Hadron Collider and the various particle accelerators as part of the CERN network. With the availability of GNSS, it gives us a number of options about how we obtain and distribute timing signals. Using GNSS allows us to obtain signals worldwide, gives us the opportunity to have a very flat distribution architecture and potentially very cost effective in some scenarios. But it creates dependencies on the satellite signals as no contract exists with these. We need views of the sky and there can be interference and jamming issues. From a network distribution perspective, we need a mechanism to distribute that through the network. We tend to use atomic clocks and GNSS at fewer locations, and as we have a reduced number of receivers, the potential cost can be lower. And we can also secure the reference clocks more easily. Standards and technology now exist to transport timing through the network, but this does require planning effort. But it allows us to turn timing on very, very quickly. All of these distribution mechanisms do require a balance of various design factors because they have performance, risk, and various total cost of ownership aspects to be considered. GNSS is an amazing system that has delivered massive benefit to the world of position, navigation and timing. However, there are limitations and these need to be understood. The recent Blackett report did a very good study in some of the critical dependencies in this space and some of the limitations. The limitations are around aspects of jamming, which is quite prevalent now, with jammers marketed as personal privacy devices. This impacts many sectors in the marketplace, and although it's not common, it does occur. But there's also other threats now, like jamming. Spoofing is now potentially a low-cost threat, and software-defined radios of a few $100s can actually implement this. And also meconning is another actual threat, where GPS or GNSS signals are intercepted and rebroadcast to confuse. So the timing world needs to understand this and actually develop techniques and processes to overcome and protect. Atomic clock performance continues to improve, and various enhanced reference clocks used for frequency and time are being developed. So typical atomic clock performance is parts in 10 to the 12 or parts in 10 to the 13 accuracy. But optical cesium clocks are being developed and other more advanced atomic clocks based on various different atomic elements. And you can see on the right there's various diagrams showing the performance of a range of different atomic clock types, either a single atomic clock or dual atomic clocks when they're brought together and what's called ensembled. And the reason for doing this is that we can bring various clocks together and protect against loss of GNSS signals. So these technologies have been standardized into telecom space and allow us to reduce the drift when we lose GNSS, for example, reduce the drift and allow us to maintain a clock and a time scale for much longer. We've covered how we generate the clock, but we have to distribute the timing through a network. And this diagram gives a very simplistic view of what we do. We take our timing reference in via a master clock, which has what's called a primary reference time clock as part of it, and we distribute it down to slave clocks. Distribution is via what's called telecom boundary clocks with physical layer frequency support, typically a multi-port switch or router, and telecom transparent clocks, typically a two-port device. The synchronization flow is master to slave down through the network to what's called the packet slave clocks, although timing messages flow in both directions. And there are various architectures to cover full and partial timing support. This combination of a physical layer consisting of what's called synchronous Ethernet and precision timing packets has been built on Ethernet technology, which has proven itself to be very adaptable to support these capabilities going in. And the picture shows a very typical provider switch router that has this timing capability built into it. Bringing this together in a phase reference model shows us how we take timing in from the sources. It could be GNSS, or there could be various atomic clocks or national timing sources, and distribute it down through the network through a chain of clocks to the end application, in this case a mobile transmitter site. So there are various points that we have to meet in terms of performance, and the key one is point E, which is the air interface of the mobile base station. But there are also requirements we have to meet in terms of particular technologies and the radio heads, in terms of how they have to work on a clustered basis. And the requirements there are quite a bit tighter, 65 up to 260 nanoseconds. If we look at the mobile piece in more detail, we can see a stylized diagram of a network with some distributed radio units. And this provides the news for 5G architecture going forward, and there are several different techniques used here, which is carrier aggregation, where we bond carriers into a bigger carrier to provide more bandwidth, and multiple input, multiple output antennas. All of these technologies are designed to provide more bandwidth down to the user to enable future applications. And how we look at the timing performance across this network is important, and it's very dependent on the RAN user case that's implemented. So you'll see there's an absolute time error from the reference source down to the antenna points, and then there are relative time errors between antennas or clusters of antennas. So in the case of mobile MIMO, multiple input, multiple output antennas, there can be tens of antennas per radio where beamforming is used, and on these systems, very tight timing requirements are required. If we look at some of the other applications that exist in the market, what's driving it? New 5G mobile gives us very massive communication capability and ultra low latency services. So that allows us to enable various human to human, human to machine, and machine to machine applications. And this industrial Internet of Things, or Industry 4.0, has three key financial objectives: how we grow revenue, how we reduce operating expense, and how we increase asset efficiency. So there are various sectors that I've listed here with various service applications and various alignment requirements that are required to make these work. Down the bottom there's a couple of examples. There's an interactive live broadcast example, and there's also a drone control over a mobile network slice example. In the drone control example, a slice was set up on a 5G network, and a mobile operator in another country has controlled a drone across that slice into another country to provide various services to demonstrate how this technology could work. And in the case of the interactive live broadcast scenario, you've not only got the challenge of maintaining the RAN, but also the challenge of the various media aspects and presenting visual live and streaming and various alignment and perception aspects to ensure that the user has a seamless experience. Using CERN as an example, at a simple level, the LH is about controlling a system very precisely using timing, accurately sensing and monitoring its operation and the data provided, and then processing this large amount of data. From a wider perspective, development of new clock and distribution technology provides the capability industry will require. Measurement and verification becomes important as the performance increases and the margin for error decreases. Development of skills and expertise becomes important, not just in a timing sense, but in tangential areas that will support the timing-aware world. So, some cross-cutting elements to consider in these new timing architectures are timing awareness to extend control of timing into the industrial space, sensors to obtain data in this time-aware world, and algorithms and processing to process this data. In the next few slides, I will talk about some of these cross-cutting elements, highlighting some areas of potential timing interest. One area is the time-aware system, or time-sensitive networking. So time-sensitive networking is part of the Ethernet standard, and it's meant to control the needs of the industrial Internet of Things and factory automation transformation, commonly called Industry 4.0. And essentially, there may be many devices, sensors, actuators, robots that need to be controlled across a factory space or a wide area. So there's a convergence of networks to support these various types of traffic under a single network infrastructure. And this leverages the ubiquitous and seamless connectivity and deterministic of course, that we'll be able to get from the 5G RAN technology, which provides an ideal platform through its high bandwidth and low latency connections. The key thing, though, is not all applications in industrial processes require access to accurate timing or even UTC timing. In some cases, it may just be local timing. It just needs to be right to itself. New atomic clock technology providing higher performance clock capabilities, providing a reduction in noise process and increased accuracy, and the ability to maintain time and frequency for longer, are potential game changer in certain sectors. Sectors requiring sensing under the surface and in the air, precise measurements, maintaining time and position in challenging environments, as well as communications can all benefit. The original cesium-based CSAC found use in the survey industry to overcome limitations in survey technology being only accurate near the surface. In a little over 10 years, there's now a potential rubidium-based solution developed by NIST. There's a potential 50 times improvement in performance over the CSAC and in a very small form factor, the factor the size of a coffee bean. Another potential sensing application is the detection of very small or stealth-based objects. For example, in traditional radar, a pulse is sent out that is then reflected from the object. If this is very small as a stealth-type technology, the reflected pulse may be very small, effectively seen as noise, or non-existent. New optical clocks with increased accuracy, along with quantum sensing that detects an object's changing gravity as it moves around in space and time, may be very, very new applications for new atomic clock technology. Distributed algorithms and processing is another area of potential interest. In the early 1990s, Barbara Lifsky of MIT talked about synchronized clocks being interesting to help improve the performance of distributed algorithms, and it would be possible to replace communication with local computation. Well, there's been a massive improvement in the performance of communication. In 1992, we might have got 622 megabits per fiber pair. Typical connectivity in 2020, 100 gigabits per wavelength was a de facto standard, and 400 gigabits, full 400 gig throughput was demonstrated in 2019 over 1,400 kilometers. So communication is no longer a problem. With increases in clock performance is no longer a problem either. So increases in bandwidth, both optical and radio, improved reliability lead to a massive improvement in how distributed algorithms may work. Combined with more accurate clocks or time distribution to timestamp and schedule, we now have potential real-time handling in software, and with the increase in computing power, including edge compute and AI, distributed algorithms and processing could have a massive, massive increase in performance. So to summarize, from the earliest times, commerce and industry have either pushed the timing world to catch up or have been playing catch up to the timing world's developments. Communications networks have provided a way to transport timing, even if that technology does not require it to operate effectively. But communications networks and timing signals are the bedrock on which many critical industries rely on. There are many developments progressing at the current time. There's clock technology, both small form factor and high performance atomic clocks, the connectivity to provide bandwidth and distribute the timing, and access to high accuracy clocks for research and development and to provide additional resilience is important. The use of timing in various ways to increase efficiency and productivity is an interesting development. The services and user cases, although they may change, ever more accurate timing is a foundation capability from which networks can do productive things. These can help increase revenue, reduce costs, or improve efficiency for all sorts of things, products and services, the way we use information, the way we communicate, the way we process information. And communications networks and the ability to transport timing have a big role to play now and in the future. There are a number of excellent presentations to follow, which will expand on some of the aspects I've covered, but I hope this presentation has been both interesting, informative, and thought-provoking.
Thank you, Mike, and a great talk there, and a good education on how communications networks and their ability to transport timing have played a pivotal role and continue to play a crucial role for the types of innovative new services and digital industries of the future. Now we're going to hear about global timescales and timing dissemination from Setnam Shamar. Setnam is a senior research scientist at NPL and has been working in time measurement and applications of timing since 1998, and is responsible for NPL's contribution to the European Space Agency's Atomic Clock Ensemble in Space Mission. So let's hear from Setnam.
Hello, I'm Setnam Shamar. I work in the National Timing Center at the National Physical Laboratory, and I'm going to talk to you about global timescales and timing dissemination. I'll first of all talk about UTC, what it is and how it's produced. Then I'll describe UTC NPL, that's the UK's representation of UTC. Then I'll talk about time dissemination techniques, and finally I'll give a brief outline of the National Timing Center, that's the NTC program. So why is timing important? Well, timing is pervasive in technology and has many applications in everyday life. Whenever there's a need for technology to be synchronized or for position to be determined, there's likely to be an essential, sometimes hidden need for timing. Here are shown some sectors in the UK with applications that use timing. For example, in the energy sector, timing enables synchronization of different parts of the electricity grid to enable it to be more efficiently monitored and controlled, as well as to locate faults more reliably. In finance, accurate timing enables the order in which financial transactions are made to be determined. While in transport, accurate timing is used in global navigation satellite systems, or GNSS, so that a GNSS receiver, such as a sat-nav in a car, can determine where it is and its speed. So what is UTC? What is Coordinated Universal Time? Well, it is the internationally agreed time standard and the basis of global civil time. You can think of it as representing the world's clock. Atomic clocks are the most stable and accurate clocks, and about 80 national timing institutes around the world submit data on comparisons between their atomic clocks to the BIPM, which is the International Bureau for Weights and Measures, where these are averaged to produce UTC. In fact, UTC is far more regular, in other words, far more stable than solar time, which was used historically and varies slightly due to the rotation of the Earth changing gradually over time. This means that noon, according to the position of the sun in the sky, would become different from noon given by UTC. It would be rather strange if time moved away from solar time. It would be rather awkward if 5 p.m. occurred at dawn, for example, so leap seconds are added to keep the two aligned. You may have heard of International Atomic Time, TAI, which is UTC without leap seconds. TAI and UTC are the most stable and accurate timescales. But what exactly do we mean by accuracy and stability? Well, an ideal accurate clock runs at the SI second rate and is in exact agreement with UTC. In the real world, however, no clock is in exact agreement with UTC, although if a clock is synchronized to UTC with a known calibrated time uncertainty, then it is said to be traceable to UTC. So how is a stable clock different from an accurate clock? Well, an ideal stable clock runs at a fixed rate. It doesn't have to be at the SI second rate, but it has to be at a fixed rate. Furthermore, a stable clock can be synchronized to another clock. It doesn't have to be synchronized to UTC. Accuracy and stability are quite interlinked concepts, but be careful not to confuse whether you have a timing accuracy requirement or a frequency stability requirement, for example. I mentioned earlier that UTC is produced by averaging the atomic clock comparison data from about 80 national timing institutes around the world. UTC is the world's timescale, but you may have noticed that it is a paper-based timescale. This means it only exists as the result of a numerical algorithm, not as a physical timing signal you can use for real-time applications. However, you can access time that is traceable to UTC from the National Timing Institutes that realize what are called national timescales. In other words, national representations of UTC, which are sometimes referred to as UTC-K timescales. These are kept in close alignment with UTC through monthly reports published by the BIPM. NPL is the National Timing Institute for the UK and maintains the UK's national timescale called UTC-NPL. UTC-NPL is the national timescale of the UK. This is run off a commercially bought hydrogen maser frequency standard. For maser, think microwave laser. UTC-NPL is a physical time point within our national timescale hardware at NPL. This is kept closely aligned to UTC through the published monthly corrections from BIPM. We are also fortunate at NPL to build and run cesium fountain frequency standards. These are basically frequency difference devices. We input a signal from the maser, and the fountain tells us how far away we are from the SI second, so that we can correct our timescale in intervals of less than a month. This arrangement allows UTC-NPL to stay within nanoseconds of UTC. But once you know the time, you have to tell everyone else what the time is. This is called time dissemination, and there are different ways of doing this. Optical fiber allows the highest accuracy, but is also the most expensive and not accessible everywhere. It's cheap to use a GNSS such as GPS or Galileo to do this, though GNSS receivers must be properly calibrated to be traceable to UTC. We have a talk later on GNSS vulnerabilities in the technical session. Another satellite-based method is two-way satellite time and frequency transfer, which uses geostationary telecommunication satellites and provides independence from GNSS. Internet time and terrestrial radio signals are often free to use, but are also of the lowest accuracy at the millisecond level, while two-way satellite time and frequency transfer and optical fiber can get down to the nanosecond level or better. In every step of the process of transferring time from a time standard to the user, the time uncertainty increases. Shown here, for example, are some time transfer techniques that may be involved in the process of getting traceable time to a home computer. Provided that it is properly calibrated, the time given by a GNSS receiver can be used to obtain time traceability to UTC higher up in the traceability chain. The GNSS receiver can then be used as the time reference for a public NTP time server, which can provide time lower in the traceability chain, for example, over the internet to a home computer. At NPL, we model the increase in uncertainty using a traceability pyramid. We have three main ways of disseminating the time to users. Our MSF radio time signal, broadcast from Cumbria, which sets the radio control clocks. Our NTP time servers for synchronizing computers, and the NPL time service. The traceability pyramid here for NPL time shows how the time uncertainty in the service increases at every step in its traceability chain. However, by using very accurate calibration techniques, the time uncertainty provided at the NPL time endpoints at customer premises can be kept to below 1 microsecond. Time dissemination methods come in two distinct types, one-way and two-way methods. In one-way methods, such as in the case of a GNSS, the timing information only travels one way from the high accuracy clock to the low accuracy clock. A GNSS receiver takes account of the time of flight of the signal from the satellite to the receiver and can be used to set the time on the low accuracy clock. Repeating with multiple satellites and averaging allows the clock comparison uncertainty to be reduced further, sometimes to as low as several nanoseconds when using a GNSS timing receiver. An example of two-way time dissemination is the Network Time Protocol, or NTP. This enables time synchronization of clocks in computer systems over packet switch networks to within a few milliseconds of UTC. Stratum 1 are the primary time servers whose clocks are synchronized to within a few microseconds of UTC, while Stratum 2 are computers whose clocks are synchronized over a network to Stratum 1 servers, and so on. NTP carries out a two-way time transfer process between a client and a server in two NTP strata. Data packets are exchanged between the client and server and vice versa, and by taking the difference of the time measurements between the packets being received and transmitted in each case, it's possible to cancel out the majority of the time delays caused by the travel time of the packets between the client and the server. This enables the difference in absolute time of the client clock from that of the server to be determined. The main source of error in the measured clock difference is due to the time delays in the exchange between client to server and server to client not being the same. This error arises because these time delays do not entirely cancel and is said to be caused by the network delay asymmetry. With NPL time, we're able to achieve better than 1 microsecond accuracy using the precise time protocol PTP, and by calibrating the network delay asymmetry using a portable atomic clock. You can go even further with calibrated White Rabbit equipment, developed at CERN for fundamental physics applications. This allows you to achieve sub-nanosecond level timing. So what future timing innovation can we expect to see in the UK? Well, the main options for timing dissemination within the UK today are through the use of GNSS signals, internet time, such as NTP, and UTC NPL, which is the UK's national timescale located at NPL. Of all the time dissemination methods possible, GNSS and internet time are the most commonly used. However, internet time using standard infrastructure is limited to millisecond level performance, while GNSS has much higher performance, but as highlighted by the Blackett review, is vulnerable to failure and disruption. The UK's national timescale, UTC NPL, is currently based on atomic clocks and timing infrastructure located on a single site at NPL. Consequently, this is a single point of failure. Future timing innovation in the UK will now be used to make this more resilient. The National Timing Centre programme, funded by the BEIS Strategic Priorities Fund, will develop a resilient timing infrastructure for the UK by building and linking a new atomic clock network distributed geographically in secure locations. It will provide innovation opportunities for UK companies by funding projects in partnership with Innovate UK. And it will respond to the specialist skills shortage in timing and synchronization solutions through training opportunities for specialists, postgraduates, and apprentices. The National Timing Centre programme will develop the Resilient Enhanced Timescale Infrastructure, RETSI. This is the resilient core underpinning the National Timing Centre programme. It will be a mesh of 4 geographically distributed linked sites with atomic clocks and other timescale hardware. It will become the source of UTC NPL, providing signals traceable to UTC NPL and to UTC. The National Timing Centre programme, or NTC, will allow access for end users through dissemination points or nodes connected to RETSI, which will allow end users to access time and/or frequency references traceable to UTC NPL. A testbed will be developed within the NTC programme, which will inform the approach needed for scaling up to deliver services to users across the UK. Thank you for listening. Let me know if you have any questions or any ideas on potential future timing applications.
Thank you, Setnam, and what a great set of first talks on timing and telecoms. We now welcome our first 3 speakers live to the Q&A session to answer questions that have been coming in from you, the audience. So I'll just start to look at the questions here. The first question I'm going to ask is going to Mike. Mike, the question came in was, what do you see as the key benefit to very high performance atomic clocks in telecoms networks?
Oh, well, thank you very much. I think in the core of our network, in the core of telecoms networks, very high performance clocks or access to very high performance clocks allows us to hold the time base or time scale within our networks. So that's a great benefit in the case where we have some of these instances of GNSS loss or GNSS potential GNSS interference. So I think, you know, that's one use. And then smaller form factor atomic clocks potentially allow us to hold the time base further down in the network when we have any failures in the network.
Okay, thank you, Mike. The next question coming in, this question's for you, Setnam. So the question that's come in here, based on your presentation, was you mentioned that the clock comparisons are being carried out between about 80 national timing institutes or labs around the world, and in order to produce UTC. So the question really is, how are those clock comparisons done? Hi, Setnam, can you hear us? We may have lost.
Sorry, just unmuted myself. So these comparisons are very important because between national timescales around the world, because they feed into UTC, the generation of the world time standard. And so because of the large distances involved between the national timing institutes around the world, we use satellites. So the most commonly used method for comparing the clocks around the world is GPS. And what happens is that comparisons are made at each laboratory using GPS and then differenced to get the comparison between the clocks. Now, the second method used is called two-way satellite time and frequency transfer, and that involves geostationary telecommunication satellites. And the good thing about that method is it's independent of GPS. That's good from a resiliency point of view, because the Blackett review highlighted the potential problems that could be caused by GNSS failure or disruption.
Okay, thank you, Setnam, for that. Next question that's coming, Leon, this one's for you. It's about the NTC program you were discussing at the start, and that Setnam mentioned again. So the question is, how can industry and academia engage on the NTC program for those that are interested in becoming part of it?
Yeah, thank you, Steve. Yeah, we are really keen to have as much of industry and academia engaged, not just to help shape the outcomes, but also to start to understand what the current requirements are, the current challenges, as well as the ones for future and emerging applications. And we have a whole series of methods to do that. One is, please do engage via our website for access to the events as they come along. But we'll be hosting a series of these webinars, workshops, as well as panel sessions. In fact, our first panel session is going to be at ITSF and broadcast on the 15th of October, where essentially it is again an interactive engagement with the community to engage on how best to make the NTC as relevant as possible for each sector across the board. We also have, I think we'll be posting a particular email address where you can contact us directly if you want to have more of a one-to-one conversation as well. But yes, please do engage and help shape this.
Thank you, Leon. And I think that's a good message. Definitely engage. It's a great program. We have questions just come in from Derwin. I think this one's Mike. If I asked for you, Mike, Derwin's asked, when creating a fiber-based resilient time network, do you see the need to provide in-service monitoring and attack detection? Is that something that's going to be important?
Yeah, I think monitoring and monitoring is always important. I think if you have to monitor everything, probably there are some concerns about maybe you've not built it properly. So I think monitoring is always good and appropriate, but if you have to monitor every single parameter and monitor every single point in the network, maybe that's adding an overhead on top of what you're trying to do as well. So I think it's getting the balance right there.
Yeah, I think that's a fair point, that balance between protection and potentially degradation of performance. We've got time, I think, for one more question. I'm going to run this across a couple of people just on the panel here to ask, because I think it's a good question. I'll start with Setnam, if you don't mind first, and then Mike will ask you to chip in. And we've only got a couple of minutes, so try to answer this quickly, although it's a difficult question. So Setnam, what do you see as the killer application for timing?
The killer application for timing. There are big things on the horizon, like autonomous vehicles, but I think the real killer application for timing is going to be something that we can't imagine right now. Something's going to turn up that no one can imagine, and it's going to completely take over, just like the internet came along. That's what's going to happen in the next 10, 20 years.
I like that. That's a good answer. And Mike, what's your thoughts on?
Yeah, I think I totally agree there. I think trying to guess what the killer application is always very dangerous. I think what we are seeing is timing awareness of services and capabilities. That will become sort of pervasive, and what we can do with that as a sort of foundation capability or an enabling capability, will spawn all sorts of applications. And what will be the killer application? Who knows? But I think there'll be many things, exciting things coming in the future.
Yeah, absolutely. And Leon, I better ask. I know the National Timing Centre will be there to help people find out what that killer application is. But what do you think?
Yeah, again, it's something that we shouldn't be speculating on. However, I really want the community to start to think about what they could do if they had signals better than GPS, with particularly the resiliency piece and the confidence it brings and that trust in time. What could you do from that perspective as perhaps a new disruptive application will come along based around that? But it's that resiliency piece, I think, that's going to be the driver for these new applications.
Perfect. Thank you all, and thank you, panel. Unfortunately, we've run out of time for this Q&A part. For the questions we couldn't get answered, we will publish responses after the event. Now we're going to go into a 5-minute break. And when we get back, we're going to hear 4 industry experts as we delve deeper on timing and telecoms with our technical focus sessions. So we'll see everyone back in 5 minutes. And we're back. Welcome back to part 2 of today's event on resilient time for the future for telecoms. We will now move on to the 4 technical focus sessions. As a reminder, the sessions are pre-recorded for quality purposes, but we will have a live Q&A at the end with all the speakers. So please do submit your questions via the Q&A facility on the webinar tool. For a lot of questions came in during the break and at the very end of last session, we're going to be trying to answer some of those online during this here period. The rest of them, as I said, we will consolidate and publish responses after this event. So we're now going to hear about testing time for 5G from Tim Frost. Now, Tim is a strategic technology manager at Calnex and has a long history in packet-based synchronization technologies. Tim is also an active contributor to the IT/UT standards. So let's hear from Tim.
Good afternoon, everybody. My name's Tim Frost from Calnex Solutions, and I'm going to be talking to you about testing time for 5G. Firstly, what is 5G? We hear a lot of hype about it in the media, and we hear that all the mobile operators are scrambling to try and deploy that at the moment. But what is it? Well, the ITU describe it as a wireless infrastructure to connect the world. So there's big ambitions in that statement. But this figure comes from a report they issued about 5 years ago when they were detailing what they expected to come from 5G. And there are basically 3 main aspects to it. Firstly is what's called enhanced mobile broadband, basically getting
Apologies, I'm just going to try and restart this slide because it's coming through a bit crackly. If you bear with me 1 second.
Good afternoon, everybody. My name's Tim Frost from Calnex Solutions, and I'm going to be talking to you about testing time for 5G. Firstly, what is 5G? We hear a lot of hype about it in the media, and we hear that all the mobile operators are scrambling to try and deploy that at the moment. But what is it? Well, the ITU describe it as a wireless infrastructure to connect the world. So there's big ambitions in that statement. But this figure comes from a report they issued about 5 years ago when they were detailing what they expected to come from 5G. And there are basically 3 main aspects to it. Firstly is what's called enhanced mobile broadband, basically getting as many bits as possible, as fast as possible, down to your mobile phone. And that can be used for things like gigabyte mobile access or replacing wired access to your homes and office with wireless access. The second aspect is what's called massive machine type communications. And this is better described as the Internet of Things, smart sensors, smart vehicles, everything connected to the internet. I was trying to buy a washing machine recently, and I noticed that many of them seem to have Bluetooth connections to your mobile phone. That's an early example of some of the Internet of Things being applied to domestic appliances. Thirdly, we have what's called ultra reliable and low latency communications. And this is for things like factory automation or self-driving cars, all these kind of mission critical applications where we need to know that the communications are getting through reliably, and also that the latency, the delay in the communication is as low as possible in order to improve throughput, say, for example, in a factory. So that's what 5G is. What are the synchronization requirements of 5G? Firstly, we have a frequency synchronization requirement. And that is simply stated that the RF carrier frequency transmitted by a base station must be transmitted within 50 parts per billion of the nominal value. So for example, if the allocated frequency is 1 gigahertz, the actual carrier frequency must be within 50 hertz of that 1 gigahertz nominal frequency. Reasons for that are, firstly, regulation and licensing. We all know that spectrum is incredibly expensive and carriers have spent millions of pounds buying spectrum and are expected to stick within the spectrum that they've bought, not transmit on anybody else's spectrum. Another reason is to prevent interference with other base stations around, and also to enable handoff for mobiles moving between cells. If, for example, a mobile is moving from one cell to another, and the second cell has a base station that's transmitting outside of that frequency accuracy requirement, the mobile might not be able to move to that cell. It might have difficulty in picking that up. So that leads to quality of service issues if there's a frequency error. Meanwhile, the user equipment itself will accept carrier frequencies that are up to 250 parts per billion out. So that's quite a big margin. The main reason for that is to accommodate Doppler effect. You all remember Doppler effect from high school physics, and it's that effect that we hear, say, from an ambulance. If it's coming towards you, you have a very high-pitched siren, and then as it passes you, the pitch of the siren gets much lower again. It's not really changing. It's a Doppler effect that's compressing and then expanding the sound waves as they come towards you or move away from you. And the same thing happens with mobile phones. If you're moving towards or away from a base station, you get Doppler effect. If you're on the TGV in France, for example, and you're going at 320 kilometers per hour, the Doppler effect might be about 300 parts per billion if you're going directly towards a base station. So you might struggle to actually maintain a call under those circumstances. We also have a time synchronization requirement. 5G networks use time division duplexing, where they alternate between downstream and upstream transmissions. So you can see here a base station transmission followed by a user equipment or a mobile phone time slot. And these time slots are separated from each other by a guard period to prevent interference. But if you have a neighboring cell, for example, the green ones here, and there's a synchronization error in the neighboring cell, you can see that slide out to the right, that second base station might start to interfere with the transmissions from the user equipment in the first cell. And that's because base stations transmit on so much higher power than user equipment that they can quickly overwhelm the transmissions there. And the same thing works in reverse. The base station 1 will interfere with equipment in the second cell. So the synchronization requirement for TDD networks is called cell phase synchronization accuracy. And simply stated, it says that all base stations with overlapping coverage areas should start their frame times within 3 microseconds of each other. And it's important to note that's a phase requirement. It's relative to the other cell, and it's not a time requirement. For example, if you have the blue base station here on the left and the green one on the right, they must be phase aligned to within 3 microseconds of each other. But it's normally implemented as a time requirement to a central clock. So if all the base stations are synchronized to the central clock to within 1.5 microseconds, that means the phase alignment requirement will always be met, and there shouldn't be any problems in the network there. Another issue that comes up sometimes is that of inter-operator synchronization. For 5G, operators want to remove the frequency guard bands to gain spectrum. So currently spectrum is allocated with frequency guard bands between the different operators. So you can see here an example. We have 3 operators that are allocated blocks of 80 megahertz of spectrum with a 20 megahertz guard band in between. And with this allocation, operator A can filter out the effects of operator B or any interference from operator B using a bandpass filter. But the problem is that's 20 megahertz of spectrum that's wasted, and operators want to gain that spectrum back. They want to be able to use the full 100 megahertz of spectrum and not have to bother with these frequency guard bands. So in order to prevent interference from operator B or from operator C, all of the different operators have to be synchronized to the same time reference. For example, the national time reference for the country, which in this country would be UTC NPL. And this might become a regulatory requirement for 5G operators to prevent interference between them. And to show how important it is, let's have a look at one operator and the interference areas for that operator. If you have two base stations, the blue and the green, you can see the coverage areas in those two circles there. And the overlapping area is just that red shaded ellipse there. And you can see that's really only at the edges of the cells. But its transmitters are probably very close to the first operator's transmitters. So when you have, if you look at their coverage areas, you can see the potential for overlap with the first operator is huge. And you get these big areas where there might be interference if one of the operators was to be synchronized to a different reference or poorly synchronized. So it's a very important issue when we come to 5G. So how do we get all these different base stations synchronized? Well, the general answer is to use GNSS as a time reference. So GNSS is the main source of time into the telecoms network, because it's a convenient means of distributing a common time reference over a wide area. Timing is generally then distributed using what's called Precision Time Protocol, or PTP, through the operator's network. And this example here shows you the architecture that's being developed by the ITU, where on the left you have a GNSS satellite transmitting time to the primary reference time clock, the PRTC. That's the primary clock within an operator's network. And then it's distributed throughout the operator's network using PTP. So we have a PTP grandmaster transmitting through the packet network to a PTP clock located at the end application. Now, as this time synchronization is so important, it's definitely necessary to measure the transmission frequency and time alignment in order to verify that it's operating within its specified parameters. And we can do that using a test set that's referenced to GNSS, and it can measure the position of the radio frames that it detects on the air and compare that to GNSS time and tell you if it's out of time alignment or frequency alignment to the GNSS signal. Now, it will need to compensate the distance from a base station antenna because it might take a few microseconds to go through the air from the base station to the test set. And the 1.5 microsecond time alignment requirement is measured at the base station antenna. So we just need to compensate for the time of flight of that radio frame. So in conclusion then, 5G has big ambitions to become an all-pervasive part of our lifestyle. If you think having 24/7 internet to your phone is an important requirement now, you've seen nothing yet. 5G is going to come to rule our lives, and if we can't get 5G, we're going to be stuck in a big way soon. It's critically dependent on accurate and reliable and traceable time. Synchronization errors threaten not just to take down one operator, but all the other operators in the same area. So it's very important. That accurate time is therefore essential to reliable mobile communications. And that's why initiatives like the National Timing Centre are going to be so important for future mobile communications. Thank you. I look forward to your questions.
Thank you, Tim. And keeping now with the same 5G theme, we want to move on now, and let's hear about the provision of time and synchronization via the 5G network from Matthew Baker. Matthew is head of radio physical layer and coexistence standardization at Nokia, where he's also a distinguished member of technical staff and has contributed to the standardization of communication technologies ranging from 3G UMTS, 4G LTE, and now 5G. So let's hear from Matthew.
Hello and welcome to this session on how 5G networks can provide timing and synchronization to the end user. My name is Matthew Baker, I'm based in Cambridge and I lead one of the radio standardization teams in Nokia's Bell Labs. You will no doubt be very familiar with the fact that an enormous and increasing number of devices and applications are already dependent on GNSS timing. Many of these are not obviously visible to the end user in areas such as telecoms, banking, and finance. But the loss of GNSS timing for any one of these applications, for whatever reason, would have devastating consequences on the ability of society to function as we've become accustomed to it. So we can say that dependence on accurate timing, currently derived from GNSS, is widespread, but at the same time critical and vulnerable. So where does 5G fit into this? 5G is not a clock. It doesn't of itself generate accurate timing. Indeed, it too needs accurate timing in order to function. But 5G is a natural and attractive mechanism for the wireless distribution of accurate timing to the end user. 5G's coverage is rapidly becoming global. It's a terrestrial system, not reliant on satellites. It is, of course, wireless, so it can penetrate anywhere with low costs of connection. It can itself be synchronized to UTC. It's highly secure and robust, and it can penetrate deeply indoors, unlike GNSS itself. Fundamentally, the distribution of accurate timing via the 5G network works like this. First, we assume that the 5G radio base stations are themselves accurately synchronized to UTC. The 5G base stations then transmit messages indicating UTC time relative to a reference time point in the 5G radio signal. The 5G radio signal is divided up into radio frames, so a radio frame boundary provides a convenient reference point. The messages can be either broadcast or unicast to specific users. Over a short distance, this mechanism alone is sufficient to enable 5G connected devices to achieve accurate synchronization to UTC. But in the latest version of 5G currently under development, it will be possible to take the radio propagation delay between the base station and the user equipment into account, and to apply compensation for that, which will enable accurate timing distribution over a wider area. So it's worth saying a bit about the evolution of support for time synchronization in 5G. The baseline version of 5G, the one that's already in commercial operation around the world today, is known as the Release 15 version of the specifications. The first time synchronization features come in Release 16, for which the specifications have just been completed. This brings the capability for accurate reference time delivery based on the generic precision time protocol, or GPTP, for time-sensitive networking, which is commonly used in Ethernet-based factory automation settings. So the controlled devices shown in this example might be robots in a production factory, with 5G providing wireless synchronization to a time source shown as the TSN end station. In Release 17, the time synchronization capability of 5G is extended to support the Precision Time Protocol, or PTP, for any application, and to provide the 5G system clock or an external clock as the time source. Additionally, the possibility of estimating and compensating for the radio propagation delay over the 5G air interface is being added. which extends the range over which 5G can distribute time synchronization wirelessly, enabling wide area synchronization. Work on the Release 17 specifications is underway now, and we're already planning for the next steps in Release 18. A key enhancement in Release 18 will be to reduce the dependency of the 5G network itself on GNSS synchronization by developing the holdover capability of the 5G network in the event of temporary loss of availability of GNSS synchronization. Highly accurate local clocks, together with standardized interfaces to enable clusters of 5G base stations to belong to and operate as the same PTP domain, will enable a holdover capability of several hours. But more than that, the 5G network could also take its timing source from another source than GNSS, such as the clock distribution being developed under the NTC project, and then distribute UTC wirelessly to the end users completely independently of GNSS. There may also be further accuracy enhancements in Release 18 by using user device position estimation to enhance the accuracy of propagation delay compensation. Putting that series of evolutions together, we can see how the achievable synchronization error from wireless time distribution by 5G is developing release by release, satisfying an ever wider set of applications with increasingly stringent requirements. So by Release 16, we can already support sufficient accuracy for most industrial automation purposes, while Releases 17 and 18 will reach the levels required for professional audio productions and smart power grid management. Let's now look in a little more detail at a couple of specific examples. First, smart power grid management. Here, the timing and resilience requirements are particularly strict, driven by the need to isolate systems within a few hundred nanoseconds. Power grid companies require a very high degree of reliability, and they're now specifying that their timing networks are not reliant on a single grandmaster clock, but in fact that they have two independent grandmasters, of which at least one is not dependent on GNSS. That's where 5G comes in, to provide a fully independent and accurate timing source over a wide area, often nationwide, without having to provide a dedicated fiber connection to every control point in the power grid. The 5G network could take its timing source from, for example, the NTC clock and distribute that nationwide to the power grid. Our second example is in finance, where there are stringent requirements to ensure the correct relative timing of financial transactions, even down to ensuring the timing integrity of every node in the system through which a transaction passes. Again, 5G can provide an independent timing source from GNSS and distribute that to the PTP domains of all relevant nodes. So, in conclusion, 5G is a natural and attractive mechanism for wireless timing distribution, with its global footprint, terrestrial infrastructure, security and robustness, and deep indoor penetration. 5G can offer accurate wireless time synchronization as a service, with sub-microsecond synchronization accuracy in releases 16 and 17, and targeting less than 250 nanoseconds in release 18. And it has full support for PTP protocols. Finally, 5G itself is becoming resilient to loss of GNSS, and it can also use other timing sources, offering timing resilience as a service in Release 18. Overall, I would dare to suggest that 5G networks are the perfect last-mile wireless distribution partner for the NTC project. Thank you.
Thank you, Matthew. Moving on to the next talk, we're now going to hear from Nir Lofer on the topic of optical channel timing. Now, Nir is a Senior Director of Product Line Management at ADVA with over 18 years of experience in developing synchronization and timing products. And Nir is responsible for the development of the Oscilloquartz next generation timing delivery and assurance product line. So let's hear from Nir.
Hello and welcome. My name is Nir Laufer, and I'm a Senior PLM Director at ADVA, Oscilloquartz Business Unit. In today's session, I would like to provide you with more details about the optical timing channels, the OTC, and the ability to deliver sub 50 nanosecond over long distance commercial WDM networks. Before we start, a short glance into Oscilloquartz, or OSA as we like to call it. OSA, it's a member of the ADVA Optical Networking Group, and it's focused in offering a sync solution for communication in government as well as enterprise applications. It has a long-standing relationship with customers worldwide since 1949. Last year, we celebrated our 70th anniversary. We are offering state-of-the-art end-to-end time and phase innovative solutions and providing time delivery and assurance excellency. Over the last couple of years, we have seen increased growth in the demand for accurate timing. We are seeing the requirement for a sub 1 microseconds coming from different verticals, mobile radio networks through financial trading, data center infrastructure and power utilities, as well as broadcast networks. They are all now requiring for some of the applications an accuracy which is in the level of sub 1 microsecond. In some cases, the requirements are even tighter and are in the range of 260 to 100 nanoseconds to some of the most demanding applications. So question which come to mind is how can we make the sync delivery more accurate and more resilient as the end application requirements are becoming tighter and more dependent on accurate phase synchronization. One of the key technologies that enable phase synchronization is GNSS or GPS. However, the use of GNSS is also subject to some known vulnerabilities and threats. Looking at some of these threats, first of all, jamming and spoofing. We have a number of occasions where jamming and spoofing, intentional or unintentional, were reported. Another threat or vulnerability is related to the GNSS segment itself. There were a few occasions where the segment itself was not operated properly, and this caused a degraded or a complete stop of the service. Last example was the Galileo blackout that lasted for almost a week. Another vulnerability is related to atmospheric disturbances such as solar activities. This could degrade the quality of time recovered from GNSS and eventually interferences from adjacent band transmitters. All these could potentially degrade or completely stop the availability of time recovered from GNSS. In order to try to overcome these challenges, ITUT came up with an architecture of clocks that allows to recover time from GNSS, but doing it with a backup. This type of clocks are called EPRTC clock, Enhanced Primary Reference Time Clocks. These clocks are typically located at the network core time-based network. Typically, there are a single-digit number of locations where these high-end clocks are installed. And these clocks, as you will see later, are combining GNSS with cesium clocks, atomic clocks, in order to guarantee that in case GNSS is no longer available, we can still maintain the service for a significant amount of time. From these core locations, timing is then provided to the network through an optical layer or an aggregation network. This could be hundreds of locations for a large operator, and the desired accuracy in this aggregation layer is to maintain a PRTC level, which is within 100 nanoseconds from UTC. And from this aggregation layer, timing is then provided to the different type of end application mentioned earlier, and maintaining the accuracy within 1 to 1.1 microsecond of time error. Looking at the core time base in more details, as mentioned earlier, these time-based sites are combining different technologies in order to make sure that we are recovering, first of all, very accurate time from GNSS. So we are using an advanced multi-band, multi-constellation GNSS receivers. We're also combining an advanced jamming and spoofing detection in these sites, and also providing some backup from peer sites. In addition, we are using the cesium clocks. This could be magnetic or optical cesium clocks that are providing very stable and accurate frequency that is used when GNSS is no longer available. All this design is made in a product or a system which is fully carrier grade redundant. So all the hardware modules should be redundant, and that guarantees that there is not a single point of failure in these core sites. When we want to deliver time from these core sites to the end application, we need to take into account the asymmetry of the network, and the asymmetry is our biggest challenge. We can see that sending the PTP 1588 packets from these core sites to the application could be done using different layers, and each of these layers can potentially introduce a different level of asymmetry. Starting from a layer 3, routers obviously add a very large asymmetry through layer 2 switches, which also add asymmetry, and eventually an OTN layer and the physical layer trying to send the PTP packets over the optical layer using a single fiber walking channel. And that is what the true time technology does, and it provides a nanosecond level of accuracy. So again, trying to go from a layer 3 to layer 1 in order to eliminate as much as possible the asymmetry of the network. So what is an optical timing channel? The optical timing channel, it's a high accuracy distribution of the 1588 PTP packets over a gigabit Ethernet, which is using a dedicated wavelength over a single fiber. The OTC minimize the constant link asymmetry due to the bidirectional transmission on a single fiber. Further compensation of the residual asymmetry can be calculated and is supported as you will see later. The optical timing channel is independent from other layers, from the optical layer and from the OTN layer. And so it's easier to add it to an existing service. And the OTC does not change the optical network engineering rules. It's just an overbuild to the optical transport layer. How this is done in practice, we can see here an example for aggregation node where we are connected through to this site using an WDM ring. We can see the east and west terminals, and on the upper picture, you could see the different wavelengths used over this WDM network. In the middle, you could see the data band where the different lambdas are used to carry the traffic from the user. And to the right, you could see the 1610 out of band wavelength, which is kept for the delivery of SYNC-key and PTP over a dedicated wavelength. This wavelength is mapped into a bidirectional channel, which is using a bidirectional transceivers. And these transceivers are then connected to a boundary clock, a high accuracy boundary clock type D, which can terminate this optical timing channel, recover time, and provide it to the line terminal where the end application are connected. We mentioned earlier the potential asymmetry. After taking into account the use of a bidirectional channel, we still use different wavelengths for transmission and reception of the PTP packets. and therefore we need to account for the different propagation delay of these two wavelengths within the fiber. Luckily, this propagation delay and corresponding asymmetry is constant and therefore can be calculated and compensated. For example, if we know the cable length and we know the type of fiber and the two wavelengths that we are using, we can accurately calculate the expected asymmetry, and this value can be compensated since it is constant and deterministic. In the following slide, I would like to show you some test results from the optical timing channel and the achievable accuracy. In this example, we are using a Paragon Neo to generate PTP traffic, which is sent into a master port connected to a chain of amplifiers and the boundary clocks over a very long spools of fiber. And eventually on the other side, on the right-hand side, we can see the last boundary clock, which is then connected back to the Paragon Neo. And the two known asymmetries that we calculated caused by the expected asymmetry of the different wavelengths over the fibers are compensated on the slave ports of each of these two boundary clocks. And as you can see at the bottom, after taking into account these expected asymmetries and the use of the optical timing channel, we were able to deliver a timer which is within 15 nanoseconds from the master port generated time. This is obviously well within the 100 nanoseconds that we defined as a target. In order to be able to build this accurate delivery of time over such a networks, we need to have the building blocks, and the key building blocks are the synchronization devices, and these are built in a Swiss knife approach, meaning that they can have different functions, starting from ePRTC through grandmaster or boundary clock, and also be able to serve different type of applications. Each one of these applications using a different variant or a different profile of the 1588 PTP, and therefore they should be able to terminate the optical timing channel and convert time to different formats where time is consumed by the end application. If you have any follow-up questions, I will be happy to answer them. Please email me to nlaufer@adva.com and I will be happy to continue the discussion with you. Thank you.
Thank you, Nir. Very good presentation. The last session today, before we go to the second live Q&A, is with John Pottle on mitigating satellite-derived time vulnerabilities. John is director at the Royal Institute of Navigation and has a long history working in the positioning, navigation and timing space, and is a fellow of the Royal Institute of Navigation. He's also president of the International Association of the Institutes of Navigation. So let's hear from John.
Great, thank you very much. Well, in just 10 minutes, I'm going to try and cover a broad subject, which is how you can apply systems thinking to time vulnerabilities in satellite-based timing systems. So the GPS time is derived from the atomic clocks on board the satellite, either rubidium or cesium, and that's linked to the UTC within 5 nanoseconds. It's called USNO UTC. And the GPS receiver, once it's locked, synchronizes to the time on the atomic clocks. And the performance that you can therefore get in terms of time in an autonomous GPS receiver is less than 40 nanoseconds, 95% of the time, typically much less than 40, maybe 10 nanoseconds. And this is extremely good, which has resulted in very broad adoption across all different critical infrastructure segments, whether it be power or transport from road, rail, air, broadcast, telecoms, and even modern applications like big data, analytics, Internet of Things, and so on. In all sorts of applications that at least I would never have thought of I believe it's GPS time is now used to timestamp clapperboards in Hollywood, and ATMs use GPS time as well. So what are the vulnerabilities? What are the sources of vulnerability? What are the roots of all of this? One of the key ones is that the satellites are a long way away, about 20,000 kilometers above the surface of the Earth, depending on the constellation. And therefore, when the signals get to the surface of the Earth, levels are extremely low. Here's a chart showing different signals, radio signals in the UK. The higher the little spike, the higher the power. And these are a range of cellular signals, radio signals, and indeed number 10 there on the right, second from right, that's Wi-Fi signals. And then look at number 7 for a minute. Number 7 just to the right of the center. Yeah, number 7 is iridium. So on the last chart, you may have seen that that is a low Earth constellation, whereas GPS is a medium Earth constellation, much further away, and more than 20 times further away. And the GPS signals are actually buried in this noise floor at the bottom here. And the receiver's job is to pull them out by correlating the signals. And that very low power level makes them quite susceptible to interference. Facet, I suppose, of GPS is that the signals are unencrypted. And the signal specifications are published. At least I'm talking here about the civilian signals that we can all use. So it's very easy to replicate them. And that's called spoofing. If you replicate the signals with the intent to provide a different time and or position, that effect is called spoofing. And in fact, there are a whole range of vulnerabilities, some naturally occurring and some man-made. Naturally occurring would include the atmospheric delays and refraction, scintillation, and ionospheric effects and so on, solar weather. But there are many other sources of vulnerability. Human error, bottom left. There was a very famous timing error introduced to GPS, 13 microseconds, which did cause impacts. Broadcast systems went off the air. And then the 3 that I've shown here as on the increase are all human derived and all on the increase. So cyber attacks over the comms interface of your receiver, interference and spoofing. And let's just look at interference and spoofing further. So this project here, Strike 3, was funded by the the GNSS agency, the GSA in Europe, and Strike 3, and deployed 50 interference detectors in the GPS L1 frequency band across 20 countries over 3 years. And they found, in round figures, 500,000 instances of interference in that band, 5% of which impacted the performance of the receiver. And that's either denying operation completely or causing an impact such as a false position and or a false time. And over the period of the study, the severity of the interference tended to increase, as well as the number of incidences observed. And there are all sorts of motivations for wanting to jam and indeed spoof, right from your unstructured hacker having a bit of quote unquote fun, through crime, up to nation state actions. And I'm sure you've all heard of incidences in the Black Sea, the Mediterranean, and around the coast of China, North Korea, South Korea. There have been many examples of interference and in some cases spoofing, some of which are unexplained, some of which are known. It's a very quick overview, and for more information, I've linked a couple of resources here, including a portal on the Royal Institute of Navigation website, where we seek to bring together reports and data and information on these types of effects I've just been talking about. So how do you approach these issues and think about how to mitigate them? Well, I haven't got time to go into detail, but in terms of a stepped approach, I'd recommend assessing system requirements, then the risks against known or expected threats, and then looking at different mitigation approaches based on that risk assessment. By a layered approach, you could think of it something like this. Potentially a global layer, including satellite navigation, a local layer, perhaps regional, a continental layer, perhaps regional, with regional satellite systems or space-based augmentation systems like EGNOS in the UK. A local level, which could involve pseudolites, local transmitters, Wi-Fi, cellular signals, and so on. And then perhaps an autonomous layer, which may include access to time over networks or fiber. And this idea of a system-of-system approach goes way back to 2001 with some of the ETSI planning guidelines then recognizing the power of combining GPS with high accuracy. And some of the approaches really can be quite simple. For example, having a GPS chain and a GLONASS chain or a Galileo chain and comparing the results. Having multiple frequencies can certainly improve accuracy, and good antennas are important. This antenna here, for example, would tend to reduce the received power level of signals at ground level while allowing in at full power level those from space. There are also on the right hand side here indicated some software based approaches, whether they be integrity monitoring within the receiver or firewalls, which would actually stop signals being emitted from the antenna if spoofing or interference is detected. Well, that's just about all I have time for, but I want to leave you with the thought that devices we're very familiar with do adopt this system-of-system layered approach very effectively indeed. And here I'd cite the mobile device. So the positioning engine is optimized for availability rather than accuracy. And if GPS is denied, then it'll switch to Wi-Fi. And if Wi-Fi is denied, it'll switch to cellular, so that you can always get a position report, even if it's not as accurate as it would be if you had good GPS. There's a great example of a layered approach in action. And then in summary, I'd recommend rationalizing this whole question in terms of a staged process, starting with system requirements, considering risks against known and expected threats and vulnerabilities, prioritizing those, and then looking at mitigations to deal with the prioritized risks. And with that, I'll conclude my remarks. Thank you.
Thank you, John, and what a great set of technical focus sessions we've just had. We do have a number of minutes. We want to now move to the second live Q&A session. We've had quite a number of questions come in. Some are being responded live on text. We will ask some of those actually questions verbally because I think some of them are worth the discussion. So the first question I want to ask is actually, John, since we've just been hearing about the satellite side of it, really a question that's came in is, how much does it help to use GLONASS or Galileo alongside GPS?
Yeah, well, thank you very much for that question. So if you use just a GPS chain, and as we've been hearing, there is, for example, a system-based error on GPS, then the system behind the receiver will feel that effect immediately, and it may be difficult to detect. If you have multiple constellations, just looking at it very simply, so you've got a Galileo chain, maybe a GLONASS chain, for example, then you can compare the position, or in this case, the time information, and if they diverge, you can raise an alert and maybe move to your holdover system. So it's in that sort of way that can help.
Thank you, John. I think we've got a question now coming in for Tim. Tim, I think you've maybe published a textual answer to this, but I think it's good to discuss. You know, why is time synchronization a problem now for 5G when it really wasn't seen as much in 4G?
Thank you. So 5G, as I said in my presentation, is a TDD-based system. So it inherently needs time synchronization in order for it to function. Whereas 4G was an FDD system, or at least it was in most countries in the world. There was a TDD version of 4G, but that's largely only being deployed in China, I believe. So for most countries in the world, it was FDD, and therefore time synchronization wasn't a problem. Frequency synchronization was a problem, and there were certainly frequency synchronization deployments available, but they didn't need to rely on GNSS so much. They could rely on physical layer synchronization and cesium clocks, whereas time synchronization inherently needs a link back to the reference time UTC.
Thanks, Tim, for that. Question coming in for Nir. Nir, in the demo or example you showed there, the question really is, it's been asked, is this technology that you showed already released and commercially available for use today?
Yes, this technology is already available and released and is used in some of the applications that mentioned earlier, especially for telecom targeting 5G and also for power utilities. I think these are the key applications where this technology is already deployed and used.
Okay, thank you, Nir. Matthew, question coming in. I think you may have responded textually, but again, I think it's worth just sharing with the audience. How would the NTC clock signal that you referred to connect to a 5G network if 5G network was going to be used for that last mile delivery? You may be on mute, Matthew.
Sorry, try that. Yep. Thank you. So the NTC clock we assume would be distributed around the country by fiber to a number of points around the country. Now, what we would expect is that clock timing would not need to be delivered to every single 5G base station. So the 5G system, if you look at the systems that are being developed, the 13 version, for example, will include the ability to synchronize a number of base stations in an area in PTP domain. So you would have one connection coming in from the NTC clock in a particular area. The 5G network then would synchronize the base stations in that area to that NTC clock, and then they would further wirelessly support the distribution of that timing over the 5G air interface. So you'd have certain points in the network, not quite clear how many you would need nationwide at the moment. That's something to be looked into, but a number of points around the country where the network would be connected, and then the 5G network would take it from there.
Thank you, Matthew. John, there's no questions been coming in on the GNSS side, and I think we've had a number of the presenters near spoke about it as well, about spoofing of jamming of GPS. But how easy is it to set up a test for spoofing or jamming of GPS to try to see how you could calibrate your systems to deal with it?
Yeah, well, thank you for the question. So spoofing gets a lot of airplay. It's not particularly widespread at the moment, and the way different receivers behave varies enormously. For example, some receivers would try to lock on to GPS and then look for other signals, and in that scenario, if the GPS signals are spoofed, it could be more vulnerable than a receiver that would actually look at all different ranging sources and have protection, such as there's a technique called RAIM, Receiver Autonomous Integrity Monitoring, which is really quite effective. So in other words, smarts within the receiver that help to identify potentially bad signals or spoof signals or jammed signals and remove them from the position calculation. So there are quite a few things to test. So I think the question was, how do you test this? Well, the simplest answer is in the laboratory. There are military test ranges, but we can't just go outside and spray test signals around. So there are many systems that allow you to test within the laboratory, generating authentic signals and spoof or jam signals, and see how your system, whether it's a GPS only system or a hybrid system with holdover clocks and so on, you can test it in a controlled way. And many people are now doing that. Thank you.
Thank you, John, and thank you, panel. We are coming close to being out of time, and I do want to pass back to Dr. Leon for a close here. So again, I just want to personally thank all of our speakers today, the attendees, and those who submitted questions. And I'm now going to hand back over to Dr. Leon Lobo, the head of the National Timing Centre program for NPL, to close out. Dr. Leon.
Thank you very much, Steve, and thank you for moderating, and to all the speakers. It was an excellent webinar as a start to the series, basically. Yeah, and thank you to everyone who's attended, as well as those who have registered. I know we've had registrants from across the globe who will be waiting on the video to be released, or the recording. And over the past hour and a bit, we've heard everything around why time, frequency, and synchronization is important for this sector, not just for our current capability and that enduring capability, but also the emerging application and challenges, and to some extent also the opportunities to leverage some of these developing capabilities, as was we heard about how 5G could potentially disseminate resilient time. But what I just want to leave you with is, please do engage, because we really want you to help support and shape the outcomes of the NTC, make it relevant for you. And to that extent, we've got a few contact points, whether it's the website for status updates on information, as well as pointers to next events, as well as the email address. We've got a live panel session at ITSF this year that'll be broadcast on the 15th of October, so please do join in. Again, that's an interactive session, as well as the rest in the series for these webinars. So yes, please do get in touch, and thank you very much for joining. Thank you.